So what we're going to do is we're going to look at how we can use our structure of our ICE table to determine the impact of the stress on a system that's at equilibrium and how that system will shift, and also determine the new equilibrium concentrations. So here we have an example where we have a system that's at equilibrium and we want to stress it so that we decrease the concentration of A by 25%. And so to stress it, what we're going to do is we're going to remove some C. Well, we know from Le Chatelier's principle, if I remove some C, then the system's going to shift in a direction to produce some C. And so it's going to shift in a forward direction to partially increase the concentration of C. So therefore, if I remove some of this, then the concentrations of my reactions will go down because my system will shift in a forward direction. So our stress is to remove some C. Now, if we look at this example, we can see that we do not have our equilibrium constant. But we are told that we have equilibrium amounts. First of all, we're told that we have moles. So when we put it into our ICE table, we have to calculate concentration. So we just take our moles and divide it by our concentration. And then we're told that these are in equilibrium concentrations. So this is my initial equilibrium concentrations. Well, even though I don't know my Kc values, since I know the equilibrium concentrations of my entities, I can calculate the value of my equilibrium constant. And so all I have to do is write my equilibrium expression and then take these equilibrium concentrations and substitute it into this expression, and I'll get the value of my equilibrium constant. So I substitute my values in and I solve and I get my Kc value. So my equilibrium constant for this reaction is 9.6. Now, let's look at how we can use our ICE table to show our stress. So we know that we have our equilibrium concentrations, and now we're going to stress it. And to stress it, I'm going to remove some C. Now, I don't know how much C I'm going to remove, and so therefore it's going to change by an unknown amount. But what I do know is that I can identify that unknown amount by a variable. Now, we're going to use the variable y because we're already using x for our change in our ICE tables, and we don't want confusion. And so we're going to say that it's going to change by y amounts, will be my stress. Now, because I'm removing C, it will be minus y. Now, since I'm only touching one of the entities, I don't need to worry about the coefficient. I took out some amount of C. I didn't take out a mole ratio amount of C. So I've only taken out y amounts of C. I have not touched either A or B in my stress. So now that my system is stressed, it's no longer at equilibrium. And it has to shift to reach equilibrium. And Le Chatelier's principle tells me that it will shift in a direction. Okay? So since I'm no longer at equilibrium, I now have initial conditions. And for my initial conditions, since I didn't touch the amounts of A or B, they're the same as they were, but my concentration of C is my initial plus my stress. And so now this would be the initial concentration of C. It has my initial plus my stress. So now we're going to change, and we know based on Le Chatelier's principle it's going to shift in the forward direction to produce some C. So therefore, we know that I'll gain here, and when it shifts in the forward direction to produce some C, it's going to consume A and B, and I'm going to decrease here. So I have a minus change here, and when I'm doing my change in my ICE table, that's when I worry about my coefficient. So for every 1 mole of B that gets converted, 2 moles of A will be lost and 2 moles of C will be produced. So now I have my new equilibrium conditions. It's my initial plus my change will give me my new equilibrium. Okay? Now, we're in a case here where we have 2 unknown variables. Right now I have an x and a y. I know my equilibrium constant, but I have 2 unknown variables. However, we were told a relationship between my initial equilibrium and my new equilibrium amounts. So, and I want my 25% decrease. So if I'm going to decrease it by 25%, that means I have 75% left. And so as a result, that allows me to determine the value of this number. Now, since I know what my new equilibrium concentration of A is going to be, that allows me to get my X value. And now that I know my X value, I can substitute it in to solve the new equilibrium value of B and get down to one unknown for C. So now I have one unknown value. Okay? And I know my equilibrium constant. I know my equilibrium expression. I have my equilibrium concentrations. A was determined by the parameter set out, which allowed me to get X to solve for B and to remove X from C's new equilibrium concentration. So now all I have to do is take these values and substitute them into my equilibrium expression and then solve for Y. And so now we get Y is equal to 0.12. Now, what's the units on this? Because it's in an ice table, the units on this is moles per liter. So this is how many moles per liter I need to remove to cause the concentration of A to decrease by 25%. But I was asked how many moles. So therefore I'm going to have to take this stress and multiply it by my volume. And so to get my number of moles of C that are removed, it's my concentration of C stress, which is this, times my volume. And I get how many moles of C I need to remove. Okay, so let's take a look at another example. Okay, so in this example, we have a 1 liter container. At equilibrium, we have these concentrations of A, B, and C. And we want to increase the concentration of A by 10%. But in this case, we're going to remove B. Okay? So I'm going to pause the video. I'm going to insert a pause. And what you can do is you can determine your equilibrium expression and look at setting up your ice table. At this point, you should be pausing the video and trying to solve on your own. Okay, so here we have our equation. Okay, we can substitute in for our ice table. We know that we have our initial concentrations, and because it's a 1 liter container, we have these. I removed some B, so it's going to be my minus Y. So now I'm no longer at equilibrium, so now these are my new initial concentrations. Because I've removed some B, my system is going to shift in the reverse direction to produce some B, so therefore it's plus on this side, and it's minus on this side. So I have my new equilibrium values. Using my initial equilibrium concentrations, I can solve for my equilibrium constant. I get that. Okay, so now using the parameters, solve for X. And pause the video again. Okay, and we know that this is our parameter. Because I want it to increase by 10%, I'm going to be 110% of my initial. So now pause the video and solve for the concentration of A. Okay, so now what we can do is we can take our initial concentration and multiply it by our change. We get this new concentration for A. We can use that to get our X value. Now once we have this, now use your X value and remove it from the equilibrium concentrations of the other two. And we get our concentration of B and our concentration of C. So now we can take these new equilibrium concentrations for A, B, and C and substitute them into our equilibrium expression to solve for Y. So again, pause the video and solve. So now we substitute our values in. Resolve. Isolate, and we get our value 1. Now remember, this is moles per liter because it's from an ice table and we're asked for how many moles. So now just take this and multiply by your volume of your container. In this case, it's a 1 liter container. And we get this many moles of B needs to be removed.